This conference will
Development
now be
Committee,
recorded.
and also he is a member in Curriculum Development Committee. Totally, he is having around 11 years of experience in teaching as well as in research. So now I would like to welcome to Dr. D. Anil Kumar Garu. Sir, thank you very much for accepting our invitation. So now I hand over to the today's chief guest, Dr. D. Anil Kumar, to the mic. I hand over the mic to the D. Anil Kumar.
Thank you very much for introducing me, Ramesh Garu.
Thank thank you very much.
Before I start my presentation, I would like to remind some good names. That is Professor Ratnakar Rao Garu, Principal of Vasavi Engineering College and Chairman of this FDP program. He was my BTech thesis advisor, and he was the one who inspired me to do some research activities during my graduation days itself. And next, Professor Ramesh Garu, Head of the Department Mechanical Engineering. Thank you for the invitation, sir. And I would like to thank the entire crew of organizing committee and coordinators who are arranging for this FDP program. Thank you. The title of this program is like numerical and experimental observations on friction stir welding process. Professor Ramesh Garu already introduced about me. I will start this program with a small motivational quote like, if we hear something, we may forget, and if we see something, we may remember. But if we do something, we will understand. This quote exactly matches with the research work. If we do, unless until we do something, it is difficult to understand what are there in it exactly. Contents of this presentation is around 5 topics like introduction to friction stir welding and simulation activity on friction stir welding and experimental studies on friction stir welding and the research challenges on this particular process, conclusions, etc. Coming to the introduction to the friction stir welding, it is a solid state welding process invented in 1991 at England in the Welding Institute. Here, what happens? A tool rotates and switches into the two welding plates. Once it completely switches into the welding plates until some extent, due to the interaction of this tool to the workpieces, the rubbing action, this rotary tool rubs on the surface of the plates. This rubbing action creates a friction. This friction is the source of heat in this particular process. So this rotary tool plunges into the workpiece and traverses along the welding line, thereby due to the heat plasticize this material, and this stirring rotating action mixes this plate and this plate together, and during the solidification action, during the cooling time, the welding occurs. That is what the happening in this particular process. For understanding, you can simply categorize this process in 4 steps. Like the first one is clamping of workpieces, rigidly clamping of these workpieces, and alignment of the tool at the center of the weld line is the first step, and plunging of the tool to the workpiece is the second step. Once it completely plunges, and after some time, around 25 to 30 seconds, until the required heat generated on the workpiece, we will keep this one at the same place. Once the required temperature produces, then we will move this tool along the weld line. So this is the traversing step, the third step. Once it reaches the end point, tool removal is the fourth step over here in the friction stir welding process. Coming to the tool of the friction stir welding process. Here, if you see, this is the friction stir welding tool, the same tool. Here, the green color portion is, we can say, like tool shoulder diameter. This tool, until it touches the tool shoulder diameter on the plates, we are going to plunge the tool on the plates. And this is the tool pin or tool probe, we can say. So this tool pin helps this welding process to mix the plasticized material. For mixing is the main objective of this particular tool pin. Whereas the tool shoulder objective, main objective is to create enough or sufficient temperature to weld these particular plates. So any variations in this particular tool may be increasing or decreasing of the tool pin diameter and tool shoulder diameter greatly influences this particular process. So, if you, for example, say this plate is around 5 to 6 millimeter. If you want to weld a plate around 10 millimeter, you need to have a bigger size of the tool compared to this one. So many factors influences this particular process, like some process variables, tool design variables, machine variables, and other variables which greatly influence this particular process. As I told you in the previous slide, variations in the dimensions of the tool will greatly influence this particular tool. That is what the tool design variables. Shoulder diameter and shoulder material and pin material will influence this particular process. And shoulder diameter, pin length, pin geometry or shape, and if the pin is having some threads, the pitch of the thread on the pin will affect this particular process either positively or negatively related to the quality of the weld. And coming to the machine variables, welding speed. Welding speed means movement of the tool from one end to the other end. That is the welding speed. Spindle speed, that is the tool rotation per minute. Plunging force, switching the tool into the workpiece, or that's what the plunging force. We can also say it as a plunge depth. Tool tilt angle, that means some cases we will keep the tool in some inclination, that is tool tilt angle. These are the some other process variables. And coming to the other variables like anvil material, in the practical application we will keep some other material as a backing plate or anvil. That anvil material will absorb some heat from the weld plates. So that means the anvil material also will influence this process. Size of the anvil or backing plate, workpiece size and thickness will influence this process. Workpiece properties also will greatly influence this process. If one wants to do a research on this friction stir welding process, we should thoroughly consider all these process variables in friction stir welding process. Coming to the zones, once the welding is completed, if we cut the weld piece and see from the thickness point side and side view, the weld zone looks like this. This is the weld zone. Some names have been given by some future researchers, like that is weld zones. The center of the welding, this is the center of the welding. This we call it as a stir zone, or we also call it as a nugget zone. Stir zone or nugget zone at the center of the welding. Just away to the stir zone, thermomechanically affected zone. That means here at this range, center of the weld, just away to the center of the weld, thermomechanically zone. Why the name called is this area is subjected to both thermally as well as mechanically affected region. That's why thermomechanically affected zone. Just somewhat away to the center of the weld, HAZ, that means heat affected zone. Only heat is affecting the material, but not mechanical effect on this particular zone. So this is what the some other names. BM means the base material, nothing influenced over here, unaffected zone or base material we can say. So there are four zones we can categorize in the weldment in friction stir welding process. Coming to the advantages and some disadvantages of this process. We can say friction stir welding is a green welding technique. Unlike conventional welding technique, it doesn't gives any toxic or harmful gases or fumes, unlike conventional technique. So it is a green welding process. You can say you can one can get some good mechanical properties in this weldment, and this process can be easily automated on a simple vertical milling machine or any CNC machine. We can automate this process. And here um, conventional welding technique, a consumable tool, always we need to change the electrode. Tool electrode will be consumable and we need to change every time in the conventional techniques. But here in FSW, tool is not consumable. Around hundreds of meters of welding length you can weld using a single tool. That's what somewhat advantage in this process. Like as I told, toxic fumes are absent in this process, and there will be very less distortion. We can say like zero distortion, and at the weld zone, no porosity been observed in the weld zone. And grain refinement takes place at the welding zone. Fine grain structure is present in this one. That is another advantage. As the welding is taking place in a solid state mode, that means the metal plate will not go to liquid state. So shrinkage will not be there in this process. Welding appearance also from the top, it looks very good. And post welding operations like conventional simple electric arc welding process, we need to do some chipping operation and filing operation and other post welding operations you need to do. But here very minimal post welding operations uh, to be done on the weldments. Some disadvantages also there in the friction stir welding process, like when you remove the tool after completion of the weld, there will be a small keyhole left over in the workpiece. That is one disadvantage. And here to hold the workpieces, we need some more forces. Clamping is somewhat difficulty in this process. We can say it as a disadvantage. And some cases tool wear, some cases tool breakage may takes place due to vibration of the machines and other effects. Sometimes wearing and breakage on the tool happens. That can be considered as a disadvantage. And coming to the applications, this process has been considered in many industrial applications like automotive applications, shipbuilding and marine industry, aerospace industry, railway industry, and some other engineering industrial sectors. This process has been considered for application. And as we have seen, many advantages in this process and less disadvantages, and applications also, wide applications are there in the industries. Many people wants to do some research and have been published in many journals throughout the years. This process invented in 1991. You see from 1996 some publications have been reported. Until it comes to 2000 year, it comes to more than 100 publications in reputed journals have been reported. This record is this data is till 2014. I hope more increment is there in the recent years too. Why only friction stir welding? Why not other welding process? Means here, particularly this process considered for non-ferrous materials like aluminum alloys, etc. So these aluminum alloys can also be welded by using some conventional welding techniques like MIG welding. gas tungsten arc welding or TIG welding. These processes also are the alternatives to weld these aluminum alloys. But here, using these conventional welding techniques, what happens here? These plates, aluminum plates, will be melted to weld in this particular process. These high temperatures and this melting of the aluminum will create some oxides. Say, for example, aluminum oxide Al2O3 formation takes place using this particular welding techniques. This aluminum oxide Al2O3 is very hard and brittle material. If these oxides forms in the center of the welding, what happens when the plate subjected to some forces, loads, this may suddenly fail. So these oxides are not preferable. And if you see, the aluminum melting point temperature is around 660 degrees centigrade, and if this Al2O3 melting point temperature will be around more than 1000 or around more than 1200 degrees centigrade, these aluminum oxides will be. So in this will not a good uh, thing for in conventional welding technique. And this aluminum is somewhat a typical material which always subjected to some uh, oxide formation, etc. So this, while cutting and while joining this aluminum, people will face some difficulties. All these difficulties like formation of aluminum oxides or intermetallic components using conventional techniques can be avoided by this particular friction stir welding process. And coming to the second topic, like simulation. Simulating a process is always preferable according to my view. Like, what it gives before doing any experiments, if you simulate the process, with the help of the simulation, we can easily find out what are the various combination of parameters to weld any particular material or size of the material. Each and every thickness of the plate of to be welded, these parameters are changing. We cannot go for always a trial experiments to do a welding operation. So if you do a simulation, just every time you can change the varying parameters. Like, if, say for example, 3 mm weld plate to 6 mm weld plate, if you change these values in the simulation, then we can obtain a possible process parameters considered useful for the doing some experiments. So simulation is always a best option to do before experiments. So in this simulation, we will see two cases: transient thermal analysis of friction stir welding on similar aluminum alloys, and transient thermal analysis of friction stir welding on dissimilar copper to aluminum alloy dissimilar welding cases. So here, before going to the simulation, main point, a point to be remembered in friction stir welding, and many people, many scientific journals also reported that to get a good weld in friction stir welding, one should obtain around 75 to 85 percentage of melting point of that particular alloy. Say for example, aluminum melting point temperature is 660 degrees centigrade. To get a good welding in friction stir welding process, one should have a temperature or heat input around 75 percentage of that particular melting point. 75 percentage of 660 degrees centigrade is required. Similarly, for different materials, we should have around 75 to 85 percentage of heat input. So using this simulation process, we can vary the parameters. One can play with the process parameters like rotation speed, traversing speed, plunging force, etc. Dimensions of the tool can be varied and check at which parameter is giving around 75 to 80 percentage of melting point of that particular metal to be welded. So this simulation helps to find out in such way. So thermal analysis in the simulation can be performed using this particular flow chart. Explains what are the steps involved in this particular simulation. Initially, you need to model the workpiece, giving the dimensions like thickness, size, etc., etc. So modeling of the workpiece. The modeled workpiece should be meshed over here. Meshing, how to do this meshing, which way to do meshing and all, we will I will show you and explain you. And after meshing, modeling and meshing, you need to give some input values over here, like you need to give a distributed heat load, and you need to consider some temperature dependent material properties, and we need to incorporate boundary conditions like initial boundary conditions and the final boundary conditions. And then after incorporating all the values in the software, then transient thermal analysis based on moving heat source will be should be performed. Then we need to get some thermal history or temperature history of the model can be obtained by incorporating all these values. Here the important things is like boundary conditions. Generally, basically two types of boundary conditions are there, like mechanical boundary conditions, like giving all degrees of freedom of the workpiece should be arrested in all the directions to avoid any rigid rotation of the entire workpiece. And the velocity of the workpiece bottom face should be arrested vertically, and the tool rotational speed is defined about z-axis. All these are mechanical boundary conditions. And thermal boundary conditions, we need to both workpiece and tool interact with environment by two modes of heat transfer here, like convective heat transfer and radiation. This is valid for all the surfaces of the tool and workpiece except the bottom face. Here, heat transfer between the workpiece and the tool is due to conduction phenomena, but incorporating conduction phenomena in software, simulating software, is somewhat difficult or tedious thing. Therefore, convective heat transfer is considered between them. And backing plate also should be neglected over here to reduce the computational calculation time of this simulation. So these are about boundary conditions. Keep the initial, always preferable to keep the initial boundary condition like room temperature around 20 degrees or 27 degrees centigrade can be keep as a initial boundary conditions. So this is about the thermal analysis. As I already told you, around 75 to 85% of melting point temperature of the metal to be welded is required temperature for doing a good friction stir welding weld. So small variations in any of the process parameters greatly influence this particular input temperature, this one. Hence, this simulation will give you an optimal process parameter to achieve input temperature. So we have developed some numerical equations for heat generation. If you see, this is the tool shoulder diameter, and this is the pin of this friction stir welding. So pin diameter and the shoulder diameter, and this is the tip of the pin. So these three regions of a friction stir welding tool gives heat generation with because of the frictional heat. This is the basic frictional heat generation equation. Keeping this as a base, we consider what we derived an equation how much heat generated over the at shoulder diameter. Qs is the heat generated at shoulder diameter. This is the equation to find out what is the amount of heat. And for the pin, tool pin, this is the equation, and the tip of the tool, friction stir welding tool, this is the equation to find out the amount of heat generated over these regions. So this sum of all these QS, QP, QT, shoulder, pin, and tip of the tool pin will give you the total heat generated in the friction stir welding process. These equations are should be incorporated in the input value. So coming to the case one here, three cases we will discuss in the simulation part, like effect of tool pin geometries of friction stir welding. That means the shape of the tool pin effect on friction stir welding, and the tool shoulder diameter, increasing and decreasing of tool shoulder diameter, what is the effect on thermal point of view, and plunging force, what is the plunging force effect on friction stir welding process, effect on FSW. Case one, effect of tool pin geometries. That means shape of the tool pin. We considered two shapes, like a simple cylindrical pin and some tapered pin over here. Diameter is 6 millimeter and length is about 5.8 millimeters. We considered these two geometries for generation of heat, and the properties we took all the some properties like rotation speed and welding speed constant, and we observed that peak temperature distribution for straight cylinder tool and taper cylinder tool around 540 and 545 degrees centigrade. Almost both the tools are giving very close peak temperature for constant, keeping all other parameters. This is the effect of tool pin geometry, tool pin shape and temperature. And case 2, effect of tool shoulder diameter. This is the tool shoulder diameter. We considered from 12 millimeter to 24 millimeter diameter, tool shoulder diameter, and we observed what kind of temperature variations, input temperature variations obtained using this this range of tool shoulder diameters. For example, if you see 12 millimeter tool shoulder diameter is giving maximum temperature at the center of the weld around 399 or 400 degrees centigrade, and for 24 millimeter shoulder diameter, 24 maximum temperature over at the center of the welding is around 521 degrees centigrade, which is within the range, like 82% of melting point temperature. So that means for welding of 6 millimeter thickness plate, one should have more than 20 millimeter shoulder diameter is the best value to be considered for FSW, pure aluminum alloy. And we tabulated all these values on some graphs, like heat distribution at the center of the building for 12 mm, 14 mm till 24 mm. This is the maximum temperatures obtained at the center of the building. And this plot shows about 16 millimeters away from the center of the building for all the different tool shoulder diameters. The third case about this is then after seeing this temperature, peak temperature, we did some experimental comparison from the numerical comparison. Almost within less than 5% of error we observed from numerical and experimental, but very close with the experimental result we observed over here. And the third case is like plunging force. We have varied from 2000 to 3250 newtons force of the tool on the workpiece, and seen about what kind of peak temperature variation. Hello?
Sir, you're audible, sir. You can continue.
Okay, sir, thank you. There is a pop-up message over here, like connection is lost. So various plunging forces. By increasing plunging forces, obtaining a peak temperature around 450 to 500 degrees, around this range, more than 3000 Newton to 4000 Newton force, you can get, one can get around 80 to 75 to 85 percentage of melting point temperature of that particular plate to be welded. So in simulation case study, these are the case one speaks about similar aluminum alloys, but this case two, like transient thermal analysis of friction stir welding on dissimilar aluminum and copper alloys will be seen over here. Like transient thermal analysis, this 3D FE analysis performed on dissimilar aluminum and copper was performed, and this here brick element considered, and with fine meshing at the center of the welding and gradually incremental meshing away to the center of the welding, and the same technique what we applied to the previously what I explained in giving initial boundary condition, finally boundary conditions, etc. We followed the same procedure for dissimilar aluminum alloys also. So we weld like this, but this simulation. Say this bottom plate is a copper plate and the top plate is like a aluminum plate. If we see this, we kept some offset of the tool. That means more portion, almost 2/3 of area of the tool pin concentrated on aluminum side, and only 1/3 of area concentrated on the copper side. And we observed the temperature for this particular process parameters, like 20 millimeter per minute welding speed and 4000 rp 4000 plunging force and 1000 rpm. We got around 465 degrees centigrade, which is within the range. This is about thermal counter from the simulation. And this is a simulation from side view, like a thickness point of view, copper side and aluminum side. This much portion, this is the center of the line. Actually, I need to keep this line out here. This is the center of the line, and this much portion on the copper and the tool pin, and this is the entire area is on aluminum side. So around 415 degrees centigrade we observed. So these temperature values from the center to the away to the center of the welding, we plotted these values on a graph for all the different various process parameters, like 16 mm per minute, 800 rpm, 3000 Newton. To we varied all these process parameters and plotted on a graph. And these are the various values for maximum temperature near to copper plate and maximum temperature at aluminum side, and these are the various process parameters. Around these parameters are giving a good temperature to get a good quality of weld. The next topic of this presentation is like experimentation of friction stir welding process. Whatever we observed in the simulation, the same things we tried to do some experiments. And here we will discuss three cases. The case one is friction stir welding of aluminum alloy by different tool pin geometries. We considered some different tool shapes, like a straight cylindrical, some tapered pin shape, and a trapezoidal shape, hexagonal shape, threaded pin shapes. And we observed which type of tool pin is giving the best quality of welding. And these are the various process parameters we considered. And we tested, we have seen the strength of this particular welds for these parameters using these tool shapes. Each tool we have conducted around 4 experiments for each tools, and we have reported these values. Like if you see, this is the base material one. Base material is having a somewhat high strength for the base material, but this friction stir welded samples, as it is maintaining the strength close to the base material, but ductility also improving over here, like this one. So for all the experiments, these are the values we plotted for stress versus strain, and these are for different tool pin geometries, hardness plotting. Around, if you see at pin center of the welding, hardness values are around here for viscous hardness testing, and outside the welding zone, this is the base material zone. It is almost the center of the welding zone and the outside out center of the welding area and base material area. Hardness values are not much variation, almost close to the um, base materials we observed in this particular welding. And we conducted some microstructural examination at heat affected zone and weld nugget zone at the center of the zone. If we see these grains, the smaller grains, like grain refinement takes place over here for this particular trapezoidal pin. See, if you see the different pin shapes, and these are the grain size values, we got it in at weld nugget at center of the weld, and at heat affected zone, these are the size of the grains we observed. Here from this, it is preferable to have a fine grain structure at the center of the weld. These two trapezoidal or tapered cylindrical pin tools are uh, giving some good grain refinement at the center of the welding over here. So this is about a trapezoidal pin for 1112 millimeter per minute parameters. These are the some microstructural observations. And the second case, friction stir welding of thick aluminum plates. So these tools, whatever we considered in the previous studies, like all these tools, from this we observed tapered tapered pin tools and trapezoidal pin tools are performing good for 6 millimeter welding of aluminum. But we wanted to see whether these tools are suitable for high thickness plates also. So we have taken around 12 millimeter thick aluminum plates, around more thickness. We tested the same tools like tapered cylindrical, some tapered pin, and trapezoidal pin. We observed for we fabricated some tools and tested for high thickness welding plates. So this is the setup of welding plate. If you see more thick welded plates, we have performed welding over here at IIT Kharagpur, and these are the tensile uh, testing samples. Some good welding obtained. See, the failure takes place just away to the center of the welding over here. So some what good quality weld joints, some bad quality welded joints which failed at the center of the weld zone for this particular parameters, like 56 welding speed and 2000 RPM and 80 and 2000 RPM. Some bad quality welded joints observed over here. The same plots, the same values we plotted over here in graphs. If you see these two values, like sky blue and green color graphs are the values of this particular bad quality welded. Rest of all showing a good. See, this is the base plate. The stress strain curve is like this, and for other welded joints, almost equivalent to the base plate observed over here. So we want to see what happened, what is the reason for this failure at the center. We wanted to see, so we did some microstructural or examination using microscope. Here we observed some defects in the center of the welding over here. We expected this kind of some throughout hole is due to because of improper mixing of material on both the sides, and there is a wormhole defect. Many researchers also reported this kind of wormhole defect in FSW process. This could be the possibility of the wormhole defect could be the high dwell time, more dwell time is the reason for the wormhole defect over here. And this, for the same things we have seen, we wanted to see the microstructural study, how the grain refinement or grain boundaries changes from different weld zones performed for this high thickness The other case, like case 3, friction stir welding of aluminum and copper alloy plates were performed experimentally and compared with the numerical result also. So here in this particular case, we consider two tool geometries. There is a threaded tool geometries and the shoulder diameter. We kept more big size of shoulder diameter around 35 millimeters shoulder diameter, and the pin diameter is around 6 millimeter. And this is the thread, left hand thread and the right hand thread tools. So these threaded tools, as this copper material is comparatively harder than this aluminum, we wanted to have a threaded tool so that mixing takes place in a good way, and we conducted the samples. These are the thermocouples. We wanted to record the temperature obtained from the weld plates. So inserting a thermocouple and connecting to the data logger, and we recorded the temperature obtained by using this friction stir welding process. These are the various tensile samples after conducting friction stir welding. And these are the hardness plots. If you observe at the center of the weld line, more hardness compared to base material. Having a base material hardness is around 125, but here at the center of the weld, more hardness was observed over here. But for few experiments, E1 is experiment 1, experiment 2. For few experiments, for experiment number 14 and 13, showing some poor hardness at the center of the weld nugget zone for right hand thread tool. For left hand thread tool experiments, more experiments were showing less hardness at the center of the weld, and we are just 2 or 3 are better hardness values obtained over here. We wanted to see what could be the reason of this one and what could be the reason of this one for right hand thread tools and left hand thread tools. The same uh, pieces we cut from the particular experiments and see optical evaluation we did, like experiment 1. There is a wormhole effect due to slower tool traverse speed, and some good welding for these particular experiment number 2 have parameters. See this tensile, ultimate tensile strength, UTS also good, and good quality welding obtained. Some other defects observed over here, and the same tensile strength also less here. And these are all good weldings and no defects observed over here. For other experiments number 9 to 16, good weld, good weld, good weld. All these are good welds, and even if you compare with the strength, strength is also more, and welding also looking somewhat good over here. And did some metallographic examination for copper and aluminum friction stir weld zone. So different zones. This is a nugget zone, thermomechanically affected zone, heat affected zone, and base materials on both the sides, called aluminum side and copper side. If we see this particular here, this is the base material of aluminium. So this particular picture is like a base material of aluminium, which is which can be seen on simple optical microscope. And this picture is a microstructure for base material of copper. And this is a thermomechanically affected zone at aluminum side and thermomechanically affected zone at copper side. And what about the center of the welding at nugget zone microstructure observed at for few samples? This is the nugget zone at the center of the welding, and we have seen it looks like this somewhat showing like some copper and aluminum is homogeneously mixed over here, and there is some lines observed over here. We wanted to know what could be these lines, and this can be observed over here, like this material movement or mixing takes place over here like this. And at some portions we observed some pieces of some copper transferred from towards aluminum side. We wanted to see what is these things, and it looks like this, and we wanted to confirm whether it is 100% copper or mixture. It's a mixture of copper and aluminum. We wanted to see, and we did some further examination using FESEM here. This is a sample around this region. At particular this region, this is the sample view, and we have selected some elements like aluminum, copper, oxygen, nitrogen, carbon, etc. This is what it is showing. The yellow portion reflects aluminum, and the copper color, this pink color is reflects copper material. So here we cannot identify what it is, where is aluminum, we cannot identify exactly. So we unhighlighted all the things, so only selected the aluminum element over here and seen. So this is the yellow portion is completely aluminum, whereas the black portion we don't know what it is. Then the next step, we unhighlight the aluminum, only highlighted the copper, which is a pink color. So then we observed copper is there over here. So leave about these portions, and if you observe at this outside of this one, both aluminum and copper are homogeneously mixed throughout at the entire weld zone. But here some more percentage of copper, still some black spots are there. That means maybe some aluminum also there, but we wanted to see how much percentage of copper over here and how much percentage of aluminum over here at the same places. So further investigation we conducted, like if you see this portion, what is the percentage of aluminum at this particular spectrum 1 area. We wanted to see what is the percentage over here, and here also what is the percentage of different two materials. So at spectrum 1, this is the spectrum 1 plot in FESEM EDX compositional analysis. So around 90 percentage of copper is present over this particular area, spectrum 1 area. So 90 percentage, only 7 percentage of aluminum is available over here. That means major, it says, we can simply say like a huge a small aluminum copper part transferred towards aluminum. But here if you see around spectrum area spectrum 2, around 58.3 percentage of aluminum observed at this particular peak, and the second highest peak is copper, around 37 percentage. That means good mixing takes place of both aluminum and copper here at the center of the building. This is what we see, though some hard aluminum pieces are transferred to other side of the aluminum, but rest of, if you neglect these particular parts, but whatever the area are there, at this is homogeneously both mixing of aluminum and copper takes place in this particular study. This kind of studies can be performed for further investigation for different materials for upcoming researchers. This is some factography study for after a tensile test, wherever the failure takes place in the tensile test. This is a pure aluminum factograph and copper side factograph. You see these cavities and peaks and valleys and of this one, which shows about a ductile failure takes place at the welding of aluminum side, and this is somewhat some brittle failure takes place towards the copper side. And this is what about experimental analysis. And this next topic is like research challenges. So what other things can be performed for those who wanted to come and work on this particular area? Some unsolved challenges or research challenges in friction stir welding. In friction stir, you have some other processes like friction stir processing, friction welding, friction stir joining, friction stir spot welding techniques are there, and friction stir. So in friction stir welding, so like very less publications or very less people reported for steels of low carbon steels or on welding of low carbon steels and mild steels using friction stir welding process has not been uh, much reported for these particular materials. And friction stir welding of dissimilar thickness sheets, say 5 mm and 6 mm, 6 mm and 7 mm, dissimilar thickness friction stir welding also very few publications reported till now. Maybe these can be taken as a challenges. And tool modifications, what kind of tool is the best for building of steels and etc. ferrous metals. Tool modifications is another challenge in friction stir welding process. And coming to the friction stir spot welding, like tool will not be moved, just like resistant spot welding. Friction stir welding, uh, friction stir spot welding technique, tool will not be traversed from after plunging. So here a keyhole is a big factor over here. So elimination or reduction of keyhole defect in friction stir spot welding is another unsolved topic in friction stir process. So coming to the processing, like friction stir processing of composite materials, metal matrix composites and nano composite materials, friction stir processing is another research challenge. Very less people published so far. And coming to the friction welding of shafts, friction welding of pipes, friction weldings of dissimilar metal shafts and dissimilar metal pipes also less published until now. And this is the latest additive manufacturing is another research area nowadays. Many people are doing using some 3D printing, etc. Some FDP, fused deposition modeling, etc. Process. People are working on that. That non metals, whatever we do using 3D printing, can be joined by using friction stir joining process. This is another research challenge, like synthetic materials or rubber materials can be joined using some friction stir joining process, like 3D printed materials, etc. So these are the unsolved research challenges in friction stir application. If you see, these are the various possible joint geometries can be done by using friction stir welding process, like butt joint, lap joint, one or the other, dissimilar thickness, small thickness to the big high thickness, T joint, corner joint, double-sided butt joint, lap fillet joint. You observe, you might be knowing all these types of welded joints, but if you come to the friction stir point of view, only butt joint is being reported much compared to other all these types of joints. Maybe you can select any material, different type of 2000 series, 2000 series, or other series of aluminum alloys, and try to do different joint geometries will be another research challenge in this particular topic. The other coming to conclusions of this particular talk, we have seen so far like how to do simulation, some experimental methods to conduct a similar material friction stir welding, dissimilar material friction stir welding, and other things we have seen, like simulating a friction stir welding process is one of the best way to select process parameters before doing experiments. The simulation helps to find out the process parameters, and this simulation also helps to minimize the cost, and it minimizes the labor power, and it minimizes the material wastage, etc. Coming to the experimental, some conclusions are framed here, like friction stir welding of low strength aluminum alloys is very much feasible welding technique of low strength alloys, and friction stir welding of dissimilar alloys was also successfully conducted for copper and aluminum, etc. Here some feasibility examination of many tool geometries or tool shapes, tool pin shapes were discussed over here. So from this particular talk, I can conclude these are the areas with these conclusions. Some experimental pictures and simulator pictures can be seen at this end of the presentation. Like this is the model of our welded plates. So if you observe, our main motto is our interest of point of interest is at the center of welding. So at the center of the welded two different plates, this is our point of interest. So do try to do a fine meshing over here at the welding zone compared to away. So here gradually increasing meshing, like rectangular meshing, brick shape meshing, and fine at the center and gradually increasing out of from the center line can be a good method to get a, good results. You see, this is the latest study we executed in recent time, like material flow modeling over here. You see even how the flash is generating a thin material is coming out once the tool is rotating and moving, traversing along the weld line. Simple, how much. So based on seeing this visual effect itself, we can observe like what kind of how much plunging force is suitable for welding of so and so thickness of material. The center of the welding, these are the different temperatures. 442 degrees centigrade at the center of the welding, and these are the other away to the center of the welding. These are the various temperatures you can observe here. See, this is the flash formation takes place conducted using Abacus software of material flow modeling. And if you see this particular picture from here to here, some flash is there, but and temperature also, peak temperature also comparatively less in this one. Here, this is a good combination of process parameters observed over here, and around 546 degrees centigrade is the maximum temperature, which is optimal good, and very less flash uh, coming out of this particular weld line is observed over here. So I'll show you how some simulational video over here. So this is a more this is the simulation video for our study, and for so if you see this experimental task we performed, so this is how the tool rotates and moves along the center of the weld line. These are the very thin, around less than 1 millimeter thick material, like a flake, aluminum flake. It is coming, and this is how one can do a friction stir welding process on a simple vertical milling machine. And if you see this welding of copper to aluminum, this is the temperature recording, like the data logger. For every second, what is the heat generation takes place. This is the data logger Agilent made. This experimental heat generation will be compared with the simulation heat, whatever we got here. So these are the thermocouples attached to the workpiece at different locations, and this is the tool moving. Traversing speeds for dissimilar friction stir welding. Welding speeds will be comparatively less for friction stir welding of dissimilar metals. So these are some recent studies we performed in the recent times, like modeling, material flow modeling, etc. And I would like to introduce my gurus who advises me for doing friction stir welding process, like Professor Pankaj Biswas, Professor Robi, Professor N.R. Mandal from IIT Kharagpur, famous person in friction stir welding process. And these are my students who are doing some work in friction stir welding process from Ethiopian students. Even a girl is interested to do this particular friction stir welding process. Thank you for your kind patience and attention. Thank you very much.
So thank you very much, sir.
Thank you, sir.
Thank you very much for your wonderful deliverance. Almost all you attracted all the participants today. So whatever you delivered the information about friction stir welding simulation, that is in transient thermal analysis of friction stir welding, similar and dissimilar alloys, and different tool pin geometries, experimentation results, and these are all which is very useful for the research scholars. And also you posted that unsolved research challenges in friction stir welding. It's very useful for the participants, those who are interested to do research in this area. And thank you very much, sir. Your presentation is very good. It is attractable to all of us. Thank you very much, sir. Now it is the queries time.
Okay.
And K. Santhi, she asked one question, sir. What are the mechanical and thermal properties of base material has to give input for simulation?
Okay, the thing is, like you need to give all, we need to incorporate all the mechanical properties like density and other thermal point of view, like temperature dependent material properties you need to incorporate in the simulation, like at different temperatures. Say for example, starting from the 50 degrees centigrade or above the room temperature from 40 degrees centigrade until 700 degrees centigrade, how the material is reacting with the temperatures, you need to give those values. Like that we will call it as a temperature dependent material properties we need to incorporate in the simulation. That is very, very important, and you will get these values if you search in Google. Some publications are there who works on temperature how the material is behaving in different temperatures. For example, for building for aluminum, compression metal properties, you can get in the Google. That's what.
Okay, sir. Okay, sir. Thank you, sir. And another one more question, sir. Sunny
Okay.
Kumar and Partha asked, in friction stir welding,
Okay.
is there any other simulation softwares, any simulation softwares available?
So, yeah, many simulation softwares are there. The thing is, if you want to do some structural simulation, then you can go for ANSYS. And if you want to do some thermal point of view, ANSYS is a standard software. And but comparatively, other softwares, ANSYS is a bit. It is not that much user friendly, but Abacus software gives free hands to the um, researchers. It is like a user friendly software, Abacus. I suggest Abacus is a good one, but and even I used ANSYS and Abacus for different applications. I felt like Abacus is easier, but still there are some other recent um, softwares are there, but computational time will takes more, and exact values you will not get in the recent topic. If
Okay,
you
sir.
do some material modeling like Fluent, ANSYS Fluent is the best option for material flow modeling, etc.
Okay, okay, sir. Thank you, sir. And
Yes, sir.
another one more question, sir. Aravind asked, is it
Mhm.
possible to use a CFD analysis tools like Fluent to do
Okay.
simulation of weldments or any other software available?
Yes, sir. That's what I said.
Okay, okay.
If anyone wants to do some fluid flow, like a material flow modeling, how the material is moving from one side to another side, from one plate to another plate, how the flash is generating, all these things can be done by Fluent. ANSYS Fluent is a
Oh,
good option
oh,
for material modeling.
thank you very much, sir. And then
Okay.
another one more question, sir.
Okay, sir.
Friction stir welding on polymers, it is possible or not? Asked by the Partha.
Yes, sir. That's what I told in the as a research challenge. The latest one, friction stir welding of friction stir joining of non-metals is a recent challenge people are doing on this one. Non-metals like rubber material, some synthetic materials. As he
Okay,
said,
yes.
polymers also now it is possible to do like this 3D printing material, other synthetics. You can do friction stir joining in this process, sir.
Uh, sir, okay, sir. Thank you, sir. And another one more question by Dhruva. In
Okay, sir.
FSW process used for 1 gram to 6 grams, all welding position welding is possible or not?
1 millimeter to 6 millimeter or
Uh,
grams? What it is?
1 gram, sir. 1
Maybe
gram to 6
millimeter.
millimeter. Okay, 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 sir. 1
Yeah,
millimeter.
I think it is a millimeter thickness. Yeah. What
Okay,
is the
sir.
question there? 1 millimeter to 6 millimeter.
1 millimeter to
All
6
the,
millimeter.
can we
All
do all
welding
the types of
position welding
joints?
possible or not?
All the joints, right?
Yes, sir. Yes, sir.
Yes, sir. Yeah. If the lesser thickness sheets are there, lap and butt is possible for lesser thickness, and even
Yes.
this dissimilar thick. These three types are possible for lesser thickness, but T joint vertical strength is not sufficient. So if it is a lesser thickness, so this is not possible for less thickness. Like less means lesser than 3 millimeters, this is not possible. Above 3 millimeters are these kind of joints are possible in FSW, sir.
Okay, okay, sir. Thank you, sir. And then another one more question from Aravind.
Okay.
What is the tool used to plot or graph the FESEM-EDX computational analysis?
Okay.
What is the tool used to plot the FESEM-EDX computational analysis?
I hope he is asking about this particular plot. Actually, I didn't plotted this one. This machine itself gave the same graph exactly, and I used the same, sir.
Okay, sir. Thank you, sir. Thank you, sir.
And
So I
the best software for doing plotting is like Origin is best plotting.
uh, okay, sir. And thank you very much, sir. I request to the participants, if there is any questions, you please contact to our resource person, Dr. D. Anil Kumar Garu. Sir, from the participants, the comments, you threw a very good attention in new scope of research, and
Thank
they're all enjoyed a lot, sir. They've given good comments. Hmm?
Thank you very much,
Thank,
all the participants. Thanks for your kind attention and patience. Thank you very much, Sir Ramesh Garu. And
thank you very much.
again, I would also like to convey my many thanks to the entire crew of organizing committee of Vasavi Engineering
Hmm.
College members. Thank you for the invitation, Ramesh Garu.
Thank you, sir. Anil, thank you very much.
thank-
Thank you, sir.
Okay. So now I request to all the participants tomorrow you have to join 10:55 a.m. the morning session. Thank you to all the participants. Thank you very much. Sarateja Garu.
Sir,
So today's assignment and attendance, sir, at which time you
Ramesh
will share.
sir,
Today
one minute.
assignment, at what time you will share in the group?
We are going to share the feedback link right now, and it will be enabled up to 6 o'clock by today evening, sir. You need to fill that now.
Okay, sir. Thank you, sir.
Okay. Thank you very
Ramesh
much.
sir, I want to
Sir, please.
Sir, please convey my greetings and many thanks to my Guruji Ratnakar Rao Garu, who is my first guide. Please convey my thanks and
Sure,
greetings to my side, sir.
sure, sir. I'll convey, sir. I'll convey, sir. Sir,
Okay,
thank
sir.
you very much for your presence over here.